Okay, next I'm delighted to welcome Sanyo Jian, Senior Software Engineer at LinkedIn, who will present secret source of stream and batch convergence at LinkedIn. Let's give Sanyo a big round of applause to welcome him to the stage.
Hello, thanks, Yuan. Thank you for that insightful talk. So, hey everyone, I am Sanal. I am a staff software engineer at LinkedIn, and I'm going to reveal the secret sauce of stream and batch convergence at LinkedIn. So, with that, let's get started. A little bit about me. So, I graduated from Northeastern in 2018. Then I joined LinkedIn and worked on the stream processing infrastructure. So, I worked across Apache Samza, Apache Beam, Apache Flink, on the managed stream processing engine, and then I led real-time embedded infra efforts at LinkedIn. So I was responsible for leading the effort building feature generation platform and the feature access platform, and lately I've been working on the stream batch unification story for LinkedIn. So that's a little bit about me. Let's dive deep into today's talk. So today's talk is going to have three parts. First, we are going to discuss LinkedIn's strategy of stream and batch unification. The part two is I'm going to deep dive into the architecture of our overall platform, which is our unified platform for both streaming and batch. And third is we are going to see how this platform powers some of the biggest use cases at LinkedIn, spawning across ads and tracking. So that's the part three. So with that, let's get started. So what is the Convergence platform, right? So my team has a mission to provide this unified platform for LinkedIn's engineers so that they can express stream or batch computations without worrying about where the data is stored. So currently, the ecosystem is kind of broken across different engines, wherein there's batch-specific engines and there's stream-specific engines, and product developers and engineers in the team, engineers at LinkedIn, have a hard time managing such different code bases, ecosystems, learning, tuning, and all of that. And we want to solve that problem. We want to make that better. Why? Because it's a lot of, there's a lot of cost associated in maintaining different engines and then teaching all your engineers at your company to learn those engines, specialize those engines, and tune those engines. So why not have a single platform that does it all? And that's what our mission is. So with that, what does it take to build this engine, to build this unified platform, right? Or what we call as the convergence platform. So basically, you need to solve two problems. The problem number one is you need to provide abstraction of unified tables where a user can just say that, hey, help me access this table, and user doesn't need to worry about where the data is stored. If the time range of access is coming from a range scan, the table comes from HDFS. And if it is coming from say real time, then it comes from Kafka. So basically you need to build the concept of storage convergence, which I'll look into on how we built it. And the second problem you need to solve is provide a unified compute API such that your users can write a code and express stream and batch computations using the same set of APIs. So these are basically the two set of problems you need to solve. Now let's look at how we solved it. So our strategy for basically stream batch unification. So first, our choice of compute convergence or the unified API, right? So let's look at what we are solving. So we have stream processing. So in stream processing, you're all aware that the data sets have this infinite out-of-order dynamic nature. And for actually processing those data sets with stream processing semantics, there's technologies like watermark, retraction, checkpointing, local state developed, so that you can process those streams and derive results, right? Now, if you compare this with batch, batch has finite data. That means you have finite organized data sets, and you need to spend energy on proactive planning such that your resource utilization is actually most efficient for processing that sort of data. And for that, we have technologies like execution stages, adaptive scheduling, and speculative execution, basically all the data skipping technologies. So now if you have to think about a unified compute engine that does both, you need to, beyond this, you also need that engine to support query optimization, scheduling, shuffle, state backend connectors, and everything. So what is the engine for this, right? And our bet is that Flink is this engine. Why? Because Flink is the leading stream processing engine in open source. We are all aware about that. Flink has Flink is TPCH compliant in terms of SQL queries. And the recent improvements in the Flink batch ecosystem plus our internal benchmarks gives us enough confidence to bet on Flink as an engine. So this gives us the choice of engine that we picked as our compute engine for Convergence. Now let's look at API. So when I joined LinkedIn, LinkedIn actually took a bet on Apache Beam as our API on top of our legacy infrastructure, which is Apache Samza. So naturally, we had Apache Beam as our choice, as one of the choices to think about when we think about an API for such unified platform. But so in order to make that decision, we did some benchmarking of Apache Beam versus Flink native APIs like Table and SQL. And in both streaming and batch benchmarks, we found that Beam is much, much slower and much more resource heavy as compared to Flink native APIs. The details of those benchmarks are attached at the end of the slides if someone wants to take a look. But basically what was a deal breaker for us is some of the benchmarks that we ran, we found that Apache Beam on top of Flink is basically 2 to 3x slower as compared to Flink native Table or SQL. So hence, our choice of API was straightforward. We had to choose Flink native APIs. So at LinkedIn, currently, we are pushing for a SQL-first strategy for streaming in general and for both this unified platform. So we are betting on Flink native Table and SQL API as our unified API. Next, right? So now we have an engine first. We have Flink, and now we have APIs, which is Flink, SQL, and Table. What's next? So I mentioned this unified table abstraction, right, which is the storage convergence problems. That means you need to have sort of abstraction which can hide the details of physical storage of those data sets. That means you need to have an abstraction, what internally at LinkedIn we call as Coda tables, which basically has data that's temporally ordered, and Coda table itself contains two different sources underneath it, one representing the snapshot, which is for historical data. That means your iceberg tables stored in HDFS, and the other part of that is a log, which is Apache Kafka for tracking the latest changes. With this unified abstraction, user gets a continuous view of data, and users only need to specify time range of access. They don't need to worry about where the data is stored. So this is what lets user write the same code so that we can use that same code and run it in a single engine without users worrying about the physical nature of that data. So that's this third thing. So this is the concept that we internally at LinkedIn call as Coda tables. Coda stands for compute and data convergence, basically. So it's a tricky name, nothing associated with the Apple TV stuff. So yeah, so the Coda table itself represents two data sources, which is iceberg in HDFS and Kafka. So that's the storage convergence. So now let's take all of this three, which is our engine API and our unified table abstraction, and understand how a convergence application runs at LinkedIn at scale. So yeah, before that, actually, let's do a little bit of deep dive into what this Coda table abstraction is, right? So this Coda table abstraction is nothing but some metadata maintained in HDFS and a catalog entry in OpenHouse. So this table metadata basically maintains snapshot log locations, schema partitions, etc. And all of that is maintained in HDFS. And we use OpenHouse as our control plane for managing this iceberg tables. So Coda internally uses OpenHouse as a catalog for catalog services. So that's this Coda table and the catalog abstraction. And then you can have a Flink catalog that can access Coda tables. And users can just do select star from coda.db.table. And the same code works in streaming as well as in batch. Yeah. So what's the benefits, right? So I think I've already mentioned this. There's two benefits of the Coda tables, right? Users only provide the logical table name and the time range of access. Basically, this is what the benefit is. Users don't need to worry about the physical location of the table. And that this enables users to easily access data and write same code for streaming and batch, right? So basically, in building this unified table abstraction, we solved following changes that we are listing here so that you guys all can take away from it. So basically, there's four things that these Coda tables solve. Table maintains time order sequencing. That means internally, Table maintains a concept of cursors, where this cursor itself can be a time or an offset-based cursor, so that you can easily switch between between batch and streaming without your users worrying about that switch. So that all things like Table or this abstraction helps us build that. The next thing that Table solves is it ensures that all the type systems, the type system in nearline, the type system in offline, and the Flink type system work with each other. That means Flink type, iceberg types, and Avro types are all in compact with each other. So that's what the type system conversion handling is. With this abstraction, we have also built abilities like filter pushdown, projection pushdown for batch, and we are looking into building this similar abilities for the next gen of pub subsystem, which is going to replace Apache Kafka at LinkedIn for streaming as well. So a table abstraction like this gives us an ability to build such optimizations. And the last thing that this Cora table solves is basically it normalizes logical schema across different sources. So because of the historical reasons, table schema from Kafka in streaming is a little bit different from the same table schema in batch because of our infrastructure needs. And we are able to basically normalize all that schema so that users don't need to worry about those problems. So we could hide all these things underneath this abstraction and make our users' life easy in writing just the code they need to write for actually expressing their business logic. So with that, I'll deep dive into our unified platform architecture. So what a convergence application looks like, right, with all the things that I've told you. So there's a source Cora table that is hiding different types of data sources. There's a sync Cora table that's also hiding different data sources. There's Flink SQL statements in the middle, and the Flink SQL statements in the middle are exercised for the streaming path and the batch path, and this is all a single application. That means this is all the same piece of code. So this is a simple convergence applications. Now let's see how does that work, let's see the architecture of our platform with the help of a convergence application. So for authoring, we have Notebook or a Flink job. We use Airflow for workflow orchestration. For compute, I already told that we have chosen Flink SQL and Flink Table as our de facto standard APIs. For runtime, we are using Flink streaming on K8s, and we use Flink batch on Yarn. And for monitoring, we use Flink History Server. We use a lot of Microsoft tools like Azure Custo and Geneva Metrics for observability and monitoring. And then for storage and unified tables, we have Apache Kafka we have Kafka topics, and we have iceberg tables in HDFS, and we use OpenHouse, which is another project that LinkedIn open source, which helps us manage those iceberg tables. So this is like the world view or the top level view of our architecture. Now let's do a deep dive into our architecture, right, on like how a convergence application works today. So a user application consists of Flink SQL statements, some UDFs, and user configs. This application can then get orchestrated or deployed via a CLI for stream processing or via an orchestrator like Airflow if the users have to create complex workflows. So that's the orchestration part. And then that deployment goes to the control plane. So we have a batch control plane, and we have a streaming control plane. For the batch side, we currently we deploy Flink applications. We deploy a Flink application in application mode on Yarn, and we use Calibon for a shuffle service. We are also exploring currently on how to actually build, we are exploring on how to support Flink batch applications on Kubernetes, because the Flink streaming currently is working on Kubernetes. So yeah, so we have Flink batch applications on Yarn, Flink streaming applications on Kubernetes, and both of those applications, because it's a convergence application, write and read from this unified table abstraction. So this is our worldview of architecture. And with our effort on building Flink batch support for building like Kubernetes support for Flink batch, we will unify our resource management layer as well as a lot of observability stack over the next few quarters. So that's our architecture. Now, is that enough? Like this unified table abstraction, unified engine, compute API, is that enough for users to really converge streaming and batch applications. We learned that in reality, that's not always the case. There's actual discrepancies between source code in streaming and batch. So let's understand with that with the use case, right? So one of the ads use case that we have had a specific requirement that they need to do some spam filtering of data, and the nearline logic to do, or like the streaming logic to do spam filtering is a little bit different than the offline or the batch logic. So for streaming, it's a gRPC lookup that helps them do a filter spam. And for batch, they do a join using, they do a left join on an iceberg table. So how would you handle something like this, right, where the actual logic itself is different? And how would you converge on this? So we proposed something called as user, like something we already kind of know, is use of temporary views, and we built something called as SQL placeholders. So what are these SQL placeholders? So these SQL placeholders are basically simple placeholders that users can just configure dynamically using config. And with the use of temporary views, they can handle such kind of discrepancies between compute or like their code in streaming and batch. So if you see here with an example, there's the nearline filtering is happening with a lookup, and the batch filtering is happening with a left join on an iceberg table. And we will let users replace this into the actual Flink SQL statement in the middle on the basis of their configurations for streaming and batch. So with this, users are able to handle those kind of discrepancies for convergence. Yeah, sorry. So with that, let's look into how users create their workflows or orchestrate workflows with our unified platform. So we enable users to have multiple workflows. That means any convergence application comes up with auto-generated workflows. And these workflows are streaming. One of the workflows is a streaming workflow where a user can just specify a table scan with a start time and a streaming job would be launched. The other workflow is just a pure batch workflow where a user can say, for start time, end time, for this table, I need to do a bootstrap or a backfill, and we spawn a batch workflow. And there is something called as hybrid, where users just specify a hybrid type workflow and a start time, and we have a logical planner that we call as the Coda planner, and that Coda planner figures out the number of batch jobs to spawn and then does a switch to the nearline job after those batch jobs have run. So all this orchestration is built using this hybrid workflow. So these workflows are auto-generated for our users, and the users can easily toggle between these workflows. So that's the workflow part. So what in the screen, you're seeing a simple example of a batch workflow in Airflow where there's multiple operators in a batch. And then the hybrid workflow that I mentioned here, which is this Coda planner that kind of generates n batch jobs and then generates a streaming job after those batch jobs have completed. So users don't need to worry about switching or doing the switchover on the boundary when they do switching from streaming and batch. So that's the hybrid workflow. So now we spoke about so many things. Now let's look at how the actual use cases at LinkedIn use convergence, right? So let's look at the ads use case. So this ads use case is a little bit tricky. It's one of the largest model data generation jobs for ads model training. Basically, what it does is it does complex joins of 4 tables, which contains ads, impressions, clicks, views, and videos. So this job is responsible for actually scoring every ad, that is ad click or ad video click or every impression that's generated on all of LinkedIn ads. So this is the logic of this job, where you have a join between ad scores and ad impressions, then there's some custom filtering, then there's a left join with click, and then there is another left join with videos. And the tricky part of this job is some of the topics here, which is this click score videos, the input of those topics or the scale of those topics varies from tens of gigabytes per second to tens of terabytes per second. So it's kind of a really tricky job. So this ads use case itself has this filtering logic difference between batch and streaming. That means, like the example I gave you guys, that they do the spam filtering using a gRPC lookup in streaming, and then they do a left join from an iceberg table in batch, and they handle this with our convergence platform. That means they run the same code in streaming and in batch. So for streaming, this job, I mean, we are all aware that Flink is a pretty scalable stream processing engine, so there's no surprise that we can run this job at scale on streaming at LinkedIn. But what I wanted to share with you guys is the scale of this job and how we are running it on batch. So we are able to do 7-day backfill under 10 hours with the improvements that we have currently made with Flink batch. The input data for this backfill is 5 petabytes. And the shuffle data scale is basically 150 to 200 terabytes of compressed data. And we are practically able to run this job at scale with Flink, with the execution mode as batch. So this is basically the resource configurations, etc. We enable adaptive scheduling. We also do, as I mentioned in the previous slides, we use Calibon for our remote shuffle service. So that helps us maintain elasticity and scalability if any faults happen, etc. So that's the details. I want to plug my colleagues' talks. We have a 3 p.m. talk detailing on how we scaled this job and how we actually used Calibon. So if you want to tune in, you would want to join that talk for understanding the details. But yeah, so this is the high-level numbers that we have made convergence not just possible, but practical at scale with one of the big use cases of ads at LinkedIn. So this is one of the examples. Now let's look at the tracking use case, right? So what's tracking? So basically, because LinkedIn is a social media platform, every activity you do with LinkedIn app, LinkedIn web, generates tracking events, right? Tracking data represents how you as LinkedIn users interact with our applications at LinkedIn. So basically, tracking data is used across LinkedIn in pretty much every product. It's used across ads, relevance models, metrics, etc. Now let's see how LinkedIn tracking data itself is derived and stored. So we have front-end clients. That means your mobile phones and your web applications have front-end clients that generates some events, which is basically generic event. And then there's the server-side events that's generated by the server. That means basically whatever application you're using on LinkedIn.com that has some associated server events. And the tracking event itself is derived by using server and the generic event side join. So there's a Flink processor that joins these two events and generates the actual tracking event, which these application teams can use. So now let's see on how do they use Convergence. So they have this as their nearline job that's generating real-time data and real-time tracking events. But beyond backfill, they have another use case or an interesting use case where we see that sometimes this generic event on the previous slide, this generic event, sometimes because it comes from all your phones, etc., and your network can go off and other problems can happen, we see that the delays, we sometimes see those topics or those messages get delayed by hours to weeks. That means we don't have the streaming data anymore, and we kind of missed that impression join in streaming, right? Because one event or one impression is came to the server basically 2 to 4 weeks late. So we see this in practical reality with LinkedIn apps. But I mean, we don't want to miss any kind of impressions, right? We don't want to miss any kind of impressions from our users because that would be really bad. So how does tracking handle this data, right? So let's look at this. So I already mentioned that there's a server and generic event. So server client side join, that's generating the custom tracking event. But beyond this and beyond backfills, we know that all this data is ETL'd into HDFS, right? So there's something that that tracking team does, that they use the same code and just tuning, changing the way changing their time ranges of which they filter their code. They actually run reconciliation jobs beyond just the backfill jobs to handle these late events, such that those missed impressions or those missed joins can get corrected or reconciliated in HDFS later for other teams to basically build applications, relevance models, etc. on. So this way, tracking team is basically doing standard scheduled reconciliation beyond backfill, beyond streaming, for actually running their applications. And all of this is same application code. There is no change in the application code. The same application runs in all 3 modes. So that's basically tracking's use of convergence beyond backfill. So yeah, with that, I think I'm coming to the end of my talk. So let's look at what it took to achieve convergence, right? So beyond unified engine, it took unified authoring, unified code config, unified table abstraction, unified testing experience. So this is all what we built. We built orchestrations, like an easy orchestration flow and tools for unified orchestration and deployments. We already told you guys that we use Flink as our unified engine and runtime. And we are also working lately towards contributing to something in Flink open source as that we could do unification of observability across streaming and batch. So that's all my talk is about, and I'm happy to take any questions. Thank you. Yeah.
Which part do you avoid fraudulent intervention? When does that come in? During convergence?
So what do you mean by fraud?
Fraudulent intervention, like, scamming the system.
Oh, I mean, we have a house security team that takes care of securing our data centers, etc. If you're suggesting something about that, yeah.
How compatible are you to ClickHouse?
ClickHouse.
How efficient are you? How fast are you compared to ClickHouse?
So we have something internally called as Venice. Venice is also open sourced by LinkedIn. That's a derived data store use case. Venice is the derived data store that stores all LinkedIn features, etc. And that's an open source project that you guys can take a look at as well. And we have a Venice connector for Convergence as well. We are also looking into exploring how to build real-time ML infrastructure that I was part of, that I led earlier onto Convergence platform next. So we'd be looking into that problem and exploring that problem space next as well. Yeah. No, so we have our own hybrid source. It's a little bit different, right? So a lot of companies adopted Kappa. I mean, you might know Uber or Netflix. They adopted Kappa, but at our scale, we have to make real batch work, right? Otherwise, like, it becomes too expensive to manage that state that grows infinite when you do something like Kappa. So that Coda table abstraction I told you about, we have our own hybrid source and our own connector internally that does that switchovers and then that management, etc. Yeah. Great question. Oh, sorry. Cool. Thank you.
Okay, thank you.
Oh, sorry.